Applications of the derivative elasticity of demand. What is elasticity of demand? Elasticity of demand measures the sensitivity of demand with a slight change in price. It is often a desire of a business owner to find out what happens to demand if price is increased. Okay, we have two ways that we talk about elasticity in general. The first is elastic, and elastic simply means that given a change in price, you have a percentage change in demand. Some people like to simply say if you increase the price, the demand is definitely affected. For inelastic, on the other hand, if a function is said to be inelastic, that just means given a change in price, you have little to no change in demand. Or if the price goes up, the demand really isn't affected. The next thing that we want to look at is our elasticity function. And our elasticity function is a function, e of x, that is given in terms of x representing the price. If x is the price, then d of x is equal to the quantity, or the demand at that price. So let's look at our function, and the way that I would read this function is the opposite of the price times the derivative of the demand function, all divided by the demand function. This function works by measuring percent. Obviously, price and quantity are two different units. So the only way really that we can compare and use the elasticity function is if we look at percent. So our elasticity function can be written a number of different ways, but if you just understand that really it is the opposite of the price times the derivative of demand all over demand. So these three different ways that I've written it below are just ways that I want you to understand they're saying exactly the same thing, and you decide which way you like to write it. The first one, written in blue, is the one that I've used already in this presentation. The second one, written in red, is exactly like the first one, except we've used P and D of P for price and demand. The third one is the one that I want to focus on for a minute because it uses a different notation for derivative. When you look at the piece that starts the function at the end, where we have E of P is equal to negative dq over dp, this piece is our derivative. So it's lining up essentially with the derivative here and the derivative here. This negative out in front, I think you can see that it's lining up with the negative that we have out in front of the functions of the first two as well. P over Q, well, P over Q is simply going to be the price over the quantity, or the price over the demand function. And we know that our demand function is simply that function that we're looking at on the denominator of each of the first representations for elasticity, d of p and d of x. So regardless of how you choose to write it, you need three important pieces. You need the price, you need the demand function, and you need the derivative of the demand function. So with elasticity, we generally find a value for our elasticity function based on a value for price. And what happens is if we get a value that is greater than 1, we say that the demand is elastic, meaning a very slight change in price will cause a change in demand. If we get a value for our elasticity function that's less than 1, then demand is said to be inelastic, which means that a slight change in price would not affect our demand. And then we have something called unit elasticity that we deal with especially when we're talking about revenue, but that's when we have our elasticity equal to 1. I think it's important to hear this in real words so that you understand what the elasticity function really means. So total revenue is increasing at those x values for which E of x is less than 1. Demand is inelastic. An increase in price will bring an increase in revenue. If demand is inelastic, then revenue is increasing. So put all of this together. Think about what this means and how elasticity relates to revenue. So if revenue is increasing when demand is inelastic, let's think about what happens if demand is elastic. Okay, before I fill in all these blanks, I want you to take a look at it just for a few seconds and see if you would be able to complete these statements. All right, so let's try this together. Total revenue is decreasing at those values for which E of x is greater than 1. Demand is elastic, and increase in price will bring a decrease in revenue. If demand is elastic, then revenue is decreasing. Another term used to describe elasticity is unit elasticity. This basically says that demand is said to be unit elastic if we get E of x equal to 1. Well, the other thing that does for us is that we know that if the demand has unit elasticity, the revenue is at a maximum. Let's go ahead and look at an example here. The demand function for the sale of t-shirts is given as Q is equal to negative p squared plus 33p, where p is the price per shirt. Find the elasticity of demand if the price is set at $10. Find the price to maximize daily revenue. Find the maximum daily revenue. And then let's explain the meaning of elasticity in the context of this example. Okay, so let's first of all just rewrite our general elasticity function so that it will be easy for us to see and use. So negative x times the derivative of our demand function all over our demand function. And following from here, simply let's go ahead and use the function that we have. So we will say E of x is equal to negative x times the derivative here, which would be negative 2x plus 33, all over our original demand function, which is negative x squared plus 33x. Continuing from here, we are simply just going to come up with the value once we substitute 10 in for x. So I'm going to stop so that we can make that calculation, but I'm also going to remind you that certainly if we're using Excel here, that we would simply have our function d of x would be represented in a cell, d prime of x would be in a cell, and x would be represented in a cell. So finding our elasticity function should be fairly easy in Excel. Okay, so finishing here, the value that I got for E of 10 was negative 13 over 23. So what that tells me is that E is less than 1. This function, for our demand function here, would be inelastic. Okay, so now let's find the price to maximize daily revenue. Well, if you remember from a previous slide, I said to maximize daily revenue is when we actually take our elasticity function and we set it equal to 1. So my elasticity function is negative x times negative 2x plus 33, all divided by negative x squared plus 33x. And we're going to take and set this equal to 1. Continuing, what's going to happen here is I recognize that I have a proportion, so I am actually going to do a little bit of distributing here across the top, and after I distribute, I will see that I end up with 2x squared plus, or excuse me, minus 33x, and I'm going to go ahead and set that equal to, because I know at this point I could go ahead and do my cross multiplication. This would be negative x squared plus 33x. And I know that I could certainly solve this using Excel. I'm going to work this algebraically for the purposes of this demonstration. So bringing everything over, it looks like I'm going to have 3x squared minus 66x is equal to 0. As I continue here, it looks like I could factor out actually a 3x. And what this is telling me is I know that I could have 3x is equal to 0, or I could have x is equal to 22. 3x is equal to 0 leads to x is equal to 0, which is basically saying if our price is 0. So we're going to discount that one, and we're going to look at this one where we have x is equal to 22. So that's telling us at $22, that would be the price to maximize our daily revenue. The next thing it's asking us to do is let's go ahead and find the maximum daily revenue. Well, to find the maximum daily revenue, we've got to first of all write our revenue function. So if we're going to write our revenue function, I think that we need to go back and say r of x is equal to, well, our original demand function for quantity was negative x squared plus 33x, and we know that we want to take and multiply that quantity by our price, which is x. Continuing this calculation, we end up with our maximum daily revenue at $5,324. Okay, so let's go ahead and summarize what we've come up with now. And what we've come up with is lots of information actually. Our original function was d of x is equal to negative x squared plus 33x. We found that our elasticity was equal to negative 13 over 23, and remember, that was when our price was equal to $10. So what we said was that our elasticity value was less than 1, therefore the function at $10 was inelastic. The price, if it was increased, would not impact our demand at that point. We further went on to find that the price that would maximize the revenue was $22, and the revenue would be, at its maximum, $5,324. Let's try one last problem. Assume that the demand for a product is Q is equal to 216 minus 2p squared, where p is our price. Let's start by finding our elasticity function, and this time I'll go ahead and use E of p, but we know that it's going to be the opposite of p times our derivative here, which would simply be negative 4p all over our original function, 216 minus 2p squared. This simplifies to 4p squared over 216 minus 2p squared. If we use that elasticity function, we really just need to look at a couple of different things. Let's determine where our price would maximize revenue. We know that that happens when our elasticity function is equal to 1. Okay, so taking our elasticity function and setting it equal to 1, I have already done this, and I know that what we have is our price that maximizes revenue is at 6. So now what we would want to do is we would want to look at two different values on either side of 6 to determine what's happening with the elasticity. So possibly we could look at a price of 1, so we could find E of 1, and I've gone ahead and looked at that as well, and that ends up being 4 over 214, which is less than 1, which tells us the values on the interval leading up to p is equal to 6 would be inelastic. If we evaluate and find the elasticity at 10, that's going to simplify to 400 over 16, which even without reducing any further, we can tell that that's greater than 1, which is telling us that the values on the upper side, or greater than 6, are going to be elastic. So to summarize this, why don't we go ahead and make a statement that basically says demand is inelastic when E is less than 1 So for this function that we're looking at, we can tell that this occurs when P is less than 6. Demand is elastic when our values of E are greater than 1, and this occurs when P is greater than 6.